In this video, we'll look at two fundamental subspaces for a matrix. So, remember what a subspace is? It's a subset of a vector space that satisfies all 10 properties that constitute a vector space. And the first subspace that we'll look at is the column space of a matrix, and the second one we'll look at is the solution space of a matrix. And at the end, we'll find out there's an intimate connection between the column space and the solution space. Well, what do we mean by the column space of a matrix A? Well, it's the span of the columns of A. So remember, span means the set of all linear combinations of vectors, where we're treating now our columns as vectors. Remember, linear combination means scaling and adding up of vectors. So essentially, we're thinking about all possible scaling and adding up of the columns of A. What space would that give us? Maybe it just gives us a plane. Maybe it gives us 3D space. Maybe it's just a single line going through the origin. So we're trying to figure out what is this space, and we call that the column space of A. So let's look at a particular example with this matrix 1, 4, 7, 2, 5, 8, 3, 6, 9. All right. And we're going to think about this matrix equation. It's this matrix equation that will help us figure out this column space of A. And this is AX equaling 0. Sometimes you'll see this is called the homogeneous or homogeneous equation, right? Homogeneous matrix equation. This homogeneous matrix equation will help us solve for the column space of A. And it'll actually help us solve for the other space that we referred to in the beginning. That is the solution space. We'll talk about that later. So right now we're trying to figure out what is the column space of our matrix A. In other words, what's the set of all linear combinations of the columns of A here? Well, by definition of matrix vector multiplication, I can rewrite this matrix equation as a linear combination of the columns of A, right? That's our definition of A times X here. Right? Take the first column scaled by x1, second column scaled by x2, third column scaled by x3, and add them all up. That's what we mean by a matrix multiplied by a vector. All right, and we have that still equal to the 0 vector. And if we actually scale and add up all the corresponding entries, we can rewrite this as a system of equations. We can write the corresponding augmented matrix, which we realized we didn't really have to go to that linear combination of columns of A and then to the system equation. We could have gone straight from just augmenting the 0 vector onto the matrix A to get a 3x4 matrix. But it's good to show, right, by definition, this is what we mean by A times X, and then we can write it as a system. And from the system, we can go to the augmented matrix. So it's good to think through that too. But in the future, you could say, oh, I'm going to augment A in the 0 vector because I know that augmented matrix represents the original matrix equation. All right, so now we can use row operations to reduce this. We can use a calculator to reduce that and get a reduced echelon form. And you get this matrix that represents the original system after doing row operations. And this means that x1 is equal to x3 and x2 is equal to negative 2x3. Right, that's the meaning of this augmented matrix. And we can let x3 be equal to a parameter t and write the solution as x1 is equal to t, x2 is equal to negative 2t, and x3 is equal to t. Right, a little review from the very beginning of our course here. This means that we have an infinite number of solutions, right? Because t can be any real number. So t could be equal to 0, and then you just have the trivial solution, which means x1, x2, and x3 are all 0. Could have t be equal to 1, and so let's consider that case. One solution of many would be 1, negative 2, 1. Right? That's when t is equal to 1. So that satisfies our matrix equation and the corresponding system equations. Right? That's one solution of many. Well, if that's the case, x1 equals 1, x2 equals negative 2, and x3 equals 1, then that means if we consider our linear combination of the columns of A, and we plug in x1, x2, and x3, we have this relationship, right? That's a way to linearly combine the columns of our matrix and have it equal to the 0 vector. which means I can rewrite and rearrange that equation to solve for 7, 8, 9, right? Just rearrange it to solve for 7, 8, 9. So subtract the 1 times the 1, 2, 3 vector, and then add over the 2 times the 4, 5, 6 vector. And this would be a good spot and stop and reflect that we've just wrote the third column of our matrix as a linear combination of the first and second column of our matrix A. So I'll just say that again. We wrote the third column, 7, 8, 9, as a linear combination of the first two columns of A, right? Scale the first column by -1, scale the second column by 2, add them up, and you get the third column. That means the third column depends on the first two columns, right? So the three columns are not linearly independent, but they're actually linearly dependent. And since you can write the third column as a combination of the first two, that means the third column is just redundant. And that means the span of the columns of A is really just all linear combinations of the first two columns. And so a basis, therefore, column 3 is in the span of column 1 and column 2. It's a linear combination of column 1 and column 2. So column 1 and column 2 form a basis for the column space of A. Right? All you need is the first two columns to describe the whole column space. Right? The set of all linear combinations of the three columns, all you need is the first two columns to describe the whole space. So the first two columns are the basis for the column space of A. So once you have that fundamental understanding of what the column space of A is, we kind of notice a pattern. So in summary, we could just look at our matrix A that we were considering. So 1, 4, 7, 2, 5, 8, 3, 6, 9. And no need to actually augment the 0 vector on there. We can just reduce this matrix and get it in reduced echelon form. And we realize the two columns that have the leading entries, the non-zero leading entries in there. So that's the first two columns. If we go back to our original matrix, look at those two columns, that forms a basis for the column space of A. Right? Now, the whole reason why that's true is based on everything that we just talked about. But you don't have to do all that work on solving the system and writing the solution and then trying to figure out one vector or one column as a linear combination of others. Right? You'll notice that this will always happen in the columns that contain the non-zero leading entries in the reduced echelon form. So in this case, columns 1 and 2. Column 1 and 2 from the original matrix constitutes the basis for the column space of A. Right? All you need are those first two columns to describe the whole column space of A. This set of all linear combinations that is the span of the columns of A. All you need is the first two columns, right? That forms a basis, right? Because all linear combinations of those first two columns, that would give you the same thing as the linear combination of all three columns, right? So you only need the first two columns. And since this basis only has two vectors, that means the dimension of the column space in this example is 2. Okay, so it's a two-dimensional space. That's the column space. That's all linear combinations of these three columns is just a 2D space. So a plane in 3D space is the column space. And we have a very special name for this dimension. We call this the rank of the matrix A. So the rank here is 2. So rank has kind of a very loaded meaning. Right? There's kind of concepts and concepts and concepts, right, all nested within each other. So rank is the dimension of the column space, but you have to know what column space means. It's the span of the columns of A, but that means you need to know what the span means. It means the set of all linear combinations of the columns of A, but then you need to know what linear combination means. It means the scaling, all scaling and adding up of the columns of A, right? So it's all like nested together like that. So rank is telling you a lot about the matrix. And so we have a single word. We use the word rank to describe all of that. All right, now we just have to talk about what we mean by the solution space of a matrix A. Right, we said this is the second fundamental subspace of a matrix, where the first one's the column space, the second one's the solution space. So the solution space, what we mean by that is all solutions to AX equals 0, right? What we call the homogeneous equation, right? Homogeneous means that we have an equal to the 0 vector on the right-hand side. So that's what we mean by homogeneous. So what are all solutions to AX equals 0? So if we go back to that example that we're considering before, so that same matrix equation, we actually already solved this, right? We did the math and figured out there's an infinite number of solutions, and we used the parameter t to describe all solutions. T could be any real number. And this is actually the solution space, right? We already know the solution to this homogeneous matrix equation. So that is the solution space. And the basis for this solution space is the vector 1, negative 2, 1. Or you could have chosen any scalar multiple of that vector, right? Because this single vector, if you think about the span of this vector, which since we only have one vector, just means all scalar multiples of this vector, right? That would describe every vector in your solution space, right? Because that's what we mean by let t be any number, right? You could think of t being 1, then 2, or 3, right? They're all scalar multiples of each other. So a basis for the solution space is the vector 1, negative 2, 1. You could have chose really any scalar multiple. It could have been 2, negative 4, 2. That could also be a basis for the solution space. But we only need one vector to describe the solution space for this matrix A, right? And so that means the dimension of the solution space is just 1. We also have a special name for that dimension. We call that the nullity, right? So the other name was rank. This one is the nullity. And so this word has loaded meaning too, right? It means the dimension of the solution space, but solution space means all solutions to AX equals 0. You have to understand what AX equals 0 mean, right? But nullity tells you a lot about your matrix also, right? It kind of has this nested meaning, right? And so in this case, the nullity is just 1. It's a one-dimensional line, right? If you think about all solutions, right? It's just a one-dimensional line going through the origin, right? When t is equal to 0, you get the 0 vector, right? The origin of your 3D coordinate system. And then you can let t be any other number. And you have different points in 3D space that would form a line going through 3D space. So you might notice that the rank plus the nullity is equal to 3, right? The dimension of the column space plus the dimension of the solution space is equal to 3. And this is the fundamental connection between the two fundamental subspaces of a matrix. The rank plus the nullity is always equal to the number of columns of A. This would be a good spot to reflect on, why is this true? Why is the rank plus the nullity, that dimension of the column space plus the dimension of the solution space, always equal to the number of the columns of A? Well, we could give a formal proof, but I'll just hint at it here. You think about reducing your matrix A, and you'll have columns that have the non-zero leading entries, right? Those ones in the non-zero leading entries in your reduced echelon form, right? Those constitute your basis for your column space. And then the other column or columns would be a basis for your solution space, right? Because that's when you can write your like x1, x2 variable, in this case of the matrix equation we considered, in terms of your other variable, which correspond to a column that didn't have a non-zero leading entry, right? So you're adding up the columns that have leading entries and the columns that don't have leading entries, right? They'll obviously just be the number of columns in your matrix A. So that means if you're just trying to figure out the dimensions of these spaces, if you find one dimension, then you automatically know the other. If you figure out the dimension of the column space is 2, then right away you know the dimension of the solution space will be 1, because they need to add up to the number of columns of our matrix. So if you have a larger matrix, maybe your matrix has 10 columns, you find out the solution space has dimension 3, that means your column space will have dimension 7. All right. Let's look at one more example to solidify these concepts. All right, say we want to find the column space and the solution space of this matrix, right, those two fundamental subspaces. Well, we saw that all we really have to do is reduce the matrix into reduced echelon form. And then the first two columns have those non-zero leading entries, right, those ones as the leading entries in the rows 1 and 2. Right, so columns 1 and 2 contain those entries. And so those corresponding columns in our original matrix form the basis for the column space of A. Right? All we need is those two columns to give us the whole column space of A. Right? If you look at all linear combinations of all 4 columns, it'll be the same as all linear combinations of the first 2 columns. Right? Because we find out that columns 3 and 4 are just redundant if we're thinking about trying to give us more space. They won't give us more space because they actually live in the space of the combinations of the first 2 columns. All right. And then if we're trying to figure out the solution space, right, what we're doing is solving AX equals 0 by definition of what it means to be the solution space of the matrix A. But to solve this, we just have to reduce that matrix again, but augment the 0 vector on the end. But we'll get the same exact reduced matrix just with the augmented 0 column at the end, because all the row operations don't affect that augmented column of zeros, right? Because it'll just be like a number times 0 plus 0, and all those row operations just keep that column as zeros. So you essentially get the same matrix just with the extra column of zeros. And we have to interpret what this matrix means. It means x1 is equal to minus 3x3 minus 2x4. So that's the interpretation of the top row, because 1x1 plus 3x3 plus 2x4 is equal to 0. So we're just rearranging to solve for x1. And the second row is telling us x2 is equal to minus 4x3. All right. Well, we have 2 variables, x3 and x4, that are determining what x1 and x2 are. So when we parameterize that, we'll need 2 parameters. We'll call them s and t. We'll let x3 be s and x4 be t, right? And that's a way to describe all solutions. And since there's a parameter s and a parameter t, that means our solution space, right, all solutions, is 2-dimensional, right? So our basis for the solution space, we take the coefficients in front of s and in front of t to get those 2 vectors. Right? The coefficients in front of s are -3, -4, 1, and 0. And the coefficients in front of t in their solution space is -2 and 0. Right? There's no t's for the x2 and no t's for the x3, so 0, 0, and then a 1. There's 1 t for x4. Right? So a way to think about that is all linear combinations of those 2 vectors, right, our 2 basis vectors, will give us all solutions to that matrix equation AX equals 0. Right? So here our dimension of the solution space is 2, the dimension of the column space is 2, right? And that should add up to be 4, right? 4 columns in our matrix, because we found out those 2 dimensions added together. All right, the rank plus the nullity should equal the columns in our matrix A. All right, well, that's the last example, and that's it for this video. Thank you.